All right, everybody. So this video will finish off the material for our second assignment this semester. Uh, Limits that involve infinity, part 2. And well, before we get into the math, let's see who the cat of the day is. There she is. Cat of the day is Luna, for no reason other than just being a cute cat. There she is. I'm looking at her right now. She keeps me company while I work in here at my desk on math. So that's Luna. I'm sure she'll be cat of the day again real soon. But anyway, let's get to the math because I think this short video will finish off everything that's in our second assignment, like I was saying. So these limits will involve infinity, all right, just like the ones in the last video, but in a different way. We'll see problems in our second assignment that are like this one right here. It'll say the limit as x goes to infinity, and then some function or formula will appear here like that. Now, if say the instructions for this one are to use a calculator, then I'll translate that as that I'm going to make a table and I'm going to see if there's some kind of pattern in the numbers, right? So all limits can be initially understood in this way, that there is such a thing as x and y. And if x does one thing, that causes y to do another. In this case, if we make the x go to infinity, we want to see what that causes the y to do, okay? Now, what does x goes to infinity look like? Well, if I start counting, I can go forever. There's no end to the numbers. For whatever number you say is the biggest number, we can add 1 to it, and we got a bigger number, so therefore there isn't a biggest number. Now, we can illustrate x going to infinity by just causing the x to get progressively bigger on a grand scale. So I might start at 10, go to 100, go to 1,000. I guess from there I could go to 10,000 if I wanted to. But anyway, it's something like that, okay? And then as with other limits we've done, this is what x going to infinity is going to look like. And I'm trying to see if there is some kind of pattern over here. The bigger the x gets, the closer the y gets to what? Now, it looks like that the bigger the x gets, the closer the y gets to 1, all right? But, I can't be absolutely certain about that, all right? I mean, I believe that. It looks pretty clear, but we could always do something like this. If we weren't sure, if we wanted to corroborate our feeling that as x went to infinity, y went to 1, then I could go up to like another bigger number, okay? So like from 1,000 to 10,000. Let's see what we get when we go to 10,000. All right, so that'll be, I'm going to calculate that number and I'm going to write it down for you. So 10,004 divided by, and I'll get 1.0006. Okay, so there we go, 1.0006. So that is even closer to 1 than this number or this number or this number, okay? Now, like, this could go on forever. It says x goes to infinity, right? So then I could do 100,000. If I really just wanted to make sure I understand that this pattern I'm seeing is correct, then go to 1,000,000 and so on. And you'll just find that every time you make this number bigger, this one gets closer to 1. All right? Okay. So that's one thing that we can do to calculate a limit, such as this. So now you have some notion of what x arrow infinity means, okay? Now, another thing we could do, though, is look at the graph, all right? And in fact, as part of our class, we should know how to read information from graphs. That's part of what, that's one of our objectives in the class, all right? So here is the graph of this function up here. This y is x plus 4 over x minus 2. Okay. That's what it looks like. Now I drew this graph by hand, and it's not to scale, okay, but it's still it is in all other aspects is what the graph looks like. Okay. So how could we see the patterns and trends and shapes on this graph in a way that can tell us what the limit as x goes to infinity is? Okay. Well, all right. So the x-axis is the horizontal axis. Okay. And for this graph, it happens to have a vertical asymptote at x is equal to 2. So there's a vertical line right here that goes through 2 on the x-axis. And it happens to have a horizontal asymptote at y is equal to 1. Okay, so in the outward direction, in the horizontal direction, the graph curves towards this line, this horizontal line that goes through 1 on the y-axis. So those are some basic features of the graph. As far as me looking at x going to infinity, that means x getting bigger and bigger and bigger, which would be further down the x-axis towards the right as we look at this graph. Now, look, say we follow the points. So x is whatever number right here. And then on that point, the x is a little bigger. And on this point, the x is a little bigger than that. And just like what do the points do if you follow them along where the x gets bigger and bigger and bigger? Now, on my graph, I can't go up to 10,000 or anything like that, but I don't have to because I can see by the shape of the graph that the bigger I choose the x to be, that follows the points this way on the curve, okay? And that makes the y-coordinate do what? That makes the y-coordinate get closer to 1, all right? Because the curve, by its nature, forms itself around this line y is equal to 1. It closes in on it gradually as you go outward either to the right or to the left. Okay, so there's x going to infinity. I can follow the points along the curve. I can see what the y-coordinate does, and it's going to go to 1. It's going to go to 1 from above, just like the numbers on our table. All these numbers were a little bit above, but getting closer to 1. So in one of my earlier videos, I said, well, the table and the graph give you the same information. That's true. Like, I'm seeing the same thing either way. I could see it a little bit quicker by looking at the graph, but it's still the same information. And me being aware that these calculations are possible, it gives me a way to think about what I see on the graph. Okay, so that's why I want to emphasize it both ways. All right, so yes, we can make a table. And if the graph is available, we can look at that too. And we can see the same thing and confirm our answers. Okay, all right, now let's do one. This one looks like a much more disagreeable formula. It's got these fractional exponents in it. X to the 5 over 2 power plus x divided by 2x minus x to the 5 over 2 power. And, you know, I have a basic scientific calculator, and I can do fractional exponents like 5 over 2. If you were to put this in your calculator, the biggest problem I see that comes up is people not using parentheses. So even though I write it down without parentheses, it may be that when you enter it in your calculator, you'll need to put parentheses around each part like this. Because the order of operations is we calculate the top and we calculate the bottom, and the last step is to divide what we get, all right? But anyway, so I did my calculations, okay? And it appears that if x goes to infinity, that would look something like this, 10, 100,000, maybe even 10,000 if I wanted to. And then I'd have to do the calculations for the y, and it looks like the closer or the larger the x gets, the bigger the x gets in the direction of infinity, the closer the y gets to -1, okay? That's what I'm seeing. And if I had any doubt that this is not getting really, really close to -1 by the time I'm at 1,000, I could go to, say, 10,000, right? Or whatever other larger number I want to. All right, now, uh, not everybody has the same kind of calculator in the class. Not everybody has the same kind of calculator as I do. If you're having trouble with your calculator confirming my numbers or otherwise getting the problems correct on our assignments, then you mention that to me. I can help you use your particular calculator. But I didn't want the focus of the videos to be how do you use every calculator in existence. All right. So you just let me know if you need help. Now, I thought that speaking of calculators, we could make use of something that everybody would have access to. So take this function right here, x 5 over 2 power plus x divided by 2x minus x 5 over 2 power. Let's put that in this. So this desmos.com/calculator, I've noticed of all the things out there, this is something that people use a lot in my class. So I'll give it to you. I think it's a pretty good tool. So I put that function in that we were just talking about, and it will graph it for me, okay? And we just talked about how we could look at the graph and determine what the limit was, okay? So my question I was just doing was, for this function, what happens if x goes to infinity? So that would mean just following the curve along the positive x-axis towards the right, okay? So I get this point, this point. See how the points are trending, okay? Where is this? I mean, by the time I am over to 8, that curve is closing in really close to whatever this number is. I can follow it over, and that's -1. -2 is right here, -1 is right here. So the larger the x gets, causes the points on the curve to travel in this direction and causes the y coordinates of those points to get closer to -1. Well, that confirms what I've seen in the table, that as x goes to infinity, y goes to -1, okay? From below, because all these points were just under -1, as is the case, this curve is just below -1, okay? Now we could do other things with this. We can look, see, if you go far enough, it's like you can't even really tell the difference between that line that goes through -1 for y and the curve itself, right? So it's like very sharply and obviously forms to -1 as x goes to infinity. Okay, so Desmos is a good tool. Make use of it if you need to. Let's see. Let's talk about one remaining rule for this assignment, and then this will be everything for that assignment. Let's talk about like a situation where we don't have to rely on a calculator or a graph, because there's a basic rule that will just tell us the answer, okay? So this rule is applicable to a limit as x goes to infinity for some rational function, a fraction, where the numerator is a polynomial and the denominator is a polynomial, okay? And I'm going to call the top polynomial A and the bottom polynomial B, just for shorthand, okay? So there are two cases that we'll talk about for determining the answer to something like this. If the degree, which is the highest exponent of the top, is equal to the degree, which again is the highest exponent of the bottom, the limit is the ratio of the leading coefficients of A over B. And I'll tell you what leading coefficient is, all right? So that's if the highest exponents on A, top and bottom, are equal, then the limit is the ratio of the leading coefficients. And we'll see an example of that in just a second. If the degree of the top is less than the degree of the bottom, where the degree in either case is the highest exponent, then the limit's going to be 0 in this case. Now let's see examples. So this is a polynomial, this is a polynomial, and this is a limit as x goes to infinity. Well, okay, what's a polynomial first? A polynomial is a function where all the terms are added or subtracted, and every term is a number times x to a positive whole number power. 9x squared, 7x to the third, 8x to the fourth, and so on. So this is a polynomial over a polynomial. Now, what did we say the degree was? Because how you determine the limit determines how the degrees at the top and bottom compare. The degree is the highest exponent. So I would say, well, for that one, the degree is equal to 2, because the highest exponent that I see is 2. And for this one, the degree is also equal to 2. Oh, so they're equal. They're both 2. They're both the same number. So it said in that case, if they're equal, see, the limit is the leading coefficient of A and B, A over B. So the leading coefficient is the coefficient of the term with the highest exponent, okay? So the leading coefficient of the top is 9, and it's not the leading coefficient just because it happens to be the one in the front. It's because it's the one that goes with the highest powered term, and the leading coefficient down on the bottom is 2. But again, 2 is not the leading coefficient because it happens to be the one in the front, because we could write these any order we want. It's because 2 is the coefficient that goes with the x that has the highest power. So 9 over 2, or you could say 4.5. Okay, so there's your limit. If you wanted to go to Desmos and look at the graph, you'd see that the further you went over to the right on the curve, the closer the curve would get to 4.5. Okay, that's what you'd see. But the rule gives us a fast way to get the answer where we don't have to do that. All right, so now let's look at this one. This one is also a polynomial over a polynomial. Okay, and it says limit x goes to infinity. So this rule seems like it would be applicable. Let's see, what is the degree here? So the degree is the highest exponent. So that would be 3, right? Largest exponent I see among these terms is 3. And here, the degree is 4, because again, 4 is the highest exponent that I see, 8x to the 4th. Okay? All right, now, so they're not equal this time. The one on the bottom is bigger than the one on the top. Well, let's see what it says. It says, in that case, if the one on the bottom, all right, degree of B on the bottom is bigger than the degree of A on the top, or if A is less than B, whatever the case is, however you want to say it, then the limit is just 0, so 0 for that one, okay? All right, now, so that's what the rule says. I'll leave you with one more way to think about it if you want to, and this is just like a way that you could think about it. It's not a proof by a rule or something like that, but with this one, it's sort of, think of it like this. This might give you a little bit of an instinct about it. If x goes to infinity, then that means the x gets really big, okay? Remember our original table that I made? Like I was going with numbers as big as 10,000 or more, okay? And we're trying to see what happens when the x gets very big. Well, so think about it like this. If, say I had 9 times 10,000 squared minus 3 times 10,000, do you think the plus 8 is going to make much of a difference? Like compared to such large numbers? Probably not. And do you think minus 25 is going to make much of a difference? You know, when the x is as big as 10,000? Probably not. All right. But then we can kind of extend the argument from there that, well, like 3x is going to be like a lot smaller than 9x squared if x is truly a very large number. So it's like the 3x doesn't matter either. Or the 8x, because again, they're going to be too small compared to 9x squared and 2x squared. So that's why the thinking focused on the leading terms and the leading coefficients, because if all this becomes insignificant as x gets really big, well, you're left with this, and then you might think, well, then the x squareds cancel, and you're left with 9 divided by 2. So that's more of a way that to help remember this as far as how it works than it is a like strict mathematical proof. But all right, I mean, I'll leave that up to you. I think it's a good enough way to think about it to remember this particular example. But other than that, the rules are what they are, and they directly tell us an answer uh, to both of these questions.